Welcome to another episode in our series on solving ODEs. In our last few episodes, we've introduced the Laplace transform and the inverse of the Laplace transform. We've gone through some few examples, and also we showed you guys on how to solve an ODE using the Laplace transform. So in this episode, what we're going to be focusing on is the convolution. So the convolution comes up naturally in solving ODEs using the Laplace transform. So before we introduce what it actually is, let us talk about how or why this would actually be useful. So looking at the Laplace transform, something that we want to notice and point out is that this fact here, that we don't have this property that we wish. It would be nice if we knew what the inverse of the Laplace of f times the Laplace of g. So what we're focusing on is we want to know what the inverse of the right is. We wish that it was this on the left. So it turns out that this statement is not true. And the reason why we do not have equality is the following. For example, take a look at a simple example. So we know what the Laplace is of 1. This is going to be 1 over s squared. However, if the above was an equality, what we could do is we can write 1 as 1 times 1. We would then, which is, this part is not true, so I'll go ahead and circle it. We would then be able to split this up as the Laplace of 1 times the Laplace of 1, and we know that this is going to be 1 over s squared times 1 over s squared. And the right is not the same thing as the left. This is a problem, so we have so we don't have an equality. If it were true, it would help us to know what this is. We want to know what the inverse Laplace of the Laplace of f times the Laplace of g. There's going to be another video coming up on how this exactly would be useful with a concrete example. For the meantime, let us search for something that would actually help us answer this question. And what would help us answer that question is going to be the convolution. So first of all, we need two functions. We need a function f and a function g. We want it to be defined for positive t or non-negative t. And the convolution is defined in the following way. So we have a function f, we have a function g, and you're going to go ahead and plug it into this integral. I want you to notice that we are integrating with respect to tau. What is fixed is t. So this is going to be a function of t. So in computing numbers, whatever you want t to be, you plug it in, and then you also plug it in at the top. So this indeed is a function of t. Something that you may want to notice is a few properties. For example, if I put a c here and put parentheses around this, where would that go? Well, that would go here. You can then easily pull it out, and you would notice that we would have c times f times the convolution of g. Another property that that you could also notice right off the back from the definition is the convolution in the reverse order. When you have g and you have you take the convolution of g and f. So what are we going to get? We're going to get a function of t. So this is actually going to be the same as this, and you can see this by considering the substitution. So if you want to show that these two are the same, what you want is this to be of a function of tau, or you can just call it u. You can consider the substitution t minus tau, plug this in, take its derivative, and switch the limits of integration, and you're going to see immediately that these two things are the same. the convolution is what we were looking for. I'm not going to show you guys that this is true, but this is a theorem that when you consider the convolution of f and g and then take its Laplace, that's going to be the same thing as the Laplace of f times the Laplace of g. This is an important fact that we will be using in our next video. But in the meantime, let's go ahead and jump to a concrete example on how to calculate the convolution of two functions. So what we're dealing here with is the convolution of t squared for t being positive and the Heaviside function. So let's go ahead and plug this into our definition. So we have here the definition in green of the convolution of two functions. So we just need to plug in directly what f is. F is t squared, so we're going to have tau squared times the Heaviside function. And remember what we're plugging in. We're plugging this in to there. So we're going to have t minus tau minus 1 d tau. Now this looks a little bit messy. So if you want, instead, we could have worked, and in fact, we're going to work with the convolution of g and f of t, in which case, what we're plugging in here is going to be the integral from 0 to t, and we're plugging in the Heaviside function, tau minus 1, times g, and in this case, g is t squared, so we're going to have t minus tau squared d tau. All right, so we need to calculate this. We want to figure out what the Heaviside function is in terms of where it's 0 and where it's 1. That's how you would approach any piecewise function when you're integrating it. So remember what the Heaviside function does. So this is our quantity, tau minus 1. When tau minus 1 is less than 0, we're going to get that our function u of tau minus 1 is going to be 0. That's what the output is. So this on the left is the same thing as tau less than 1. So when we have tau less than 1, our function spits out 0. And let's go ahead and look at the other side. So when tau minus 1 is greater or equal to 0, what we're going to spit out of our function is going to be 1. So this is the same thing on the left as 1 less than or equal to tau. How is this useful? Well, let me go ahead and change my colors here. Well, we're interested when t. We're calculating what the convolution is. And the convolution really depends on what t is. So, for example, if t... So, in calculating this integration, we must remember that tau is in between 0 and t. So let me write that here. So tau is in between t and 0. So if t, so let's go ahead and write this. So if t is less than 1, what do we know about tau? Then tau is going to be less than 1, which is going to imply that our function is going to spit out 0. So in this situation, then g convolution with f of t is going to spit out 0. So then we got that part calculated. So now we want to move on to what happens when t is greater than 1, greater or equal to 1. So now in that case, what we're going to do is we're going to go ahead and look at this integral. So let me go ahead and copy this integral. Here we go. And let's go ahead and paste it here. And so let's go ahead and now split up our integration. So we're going to have the integration between 0 and 1, and then between 1 and whatever t is. Then we're going to copy what we're integrating here and here. Shrink it up. And this is with respect to tau, d tau. So in this section on the left, we've already concluded what our function is. This is going to be 0. And so this entire thing here just disappears. So then what we need to do is we want to focus on what is remaining. So the remaining portion, this function here is going to spit out 1. So in that portion, what we have here is 1 times t, and then, we're integrating from 1 to t. We have 1 times t minus tau squared d tau. We're looking for the antiderivative. Now we can do a substitution, or we could just look for the antiderivative, quantity squared. Well, we want to raise this to the third power and divide by 3, plug in what we have in the inside, and then what we need so this is the antiderivative of u squared. But then we need to consider chain rule, and if you take the derivative of this, we're not going to get this. There's a negative missing, so I just put a negative there. And then we want to evaluate this at 1 and t. So let's go ahead and do that. So when we evaluate this at t, we're going to get 0. So then we want to subtract what happens when we plug in. So when we subtract, the negatives cancel, and we have t minus 1 to the third power divided by 3. So that there is the convolution of f and g. But this here is when t is greater or equal to 1. So what we want to write is the convolution of f and g. It's going to be this, t minus 1 to the third power divided by 3 times the heaviside function of t minus 1. This is going to guarantee that we have 0 before 1, and at 1 we get exactly what we wanted. So thank you for joining us.